Okay, so hi again. Hope you had a nice lunch. So in this second part, we're going to talk about these very new topic, which are called Sheaf neural networks. And we're going to see essentially, so the big picture is the one I was describing before. And I was mentioning how these graphs, they are essentially kind of discrete objects. They don't necessarily have like a continuous version. So then how can we kind of do some interesting things on these spaces, right? Because we don't have much structure. And it turns out we don't need that much structure to do interesting things, as in like geometric structure, that's what I mean. And we're going to see how we can kind of fill in like very simple way that question mark, and by taking this topological perspective. And essentially what we're going to do is we're going to just start with looking at the graph as a topological space and work our way upwards towards things that look a bit like something that's like a Riemannian manifold. Obviously it can't be because it's a graph, but it has some of those similar concepts. Now you've already seen these things. I'm not going to go through this again, but yeah, again, just open sets on a space. And what I want to show you is that we can think of graphs as topological spaces. So essentially, if we take the star operator that I was mentioning in the previous talk for cell complexes right at the end, we can put some open sets on the graph. So for this graph, well, this is kind of just a zoomed in version on just looking at a single edge in this graph. And we can see here 3 open sets. So we have the star of this orange node, and it's basically all these kind of all the points in this orange region. We have the star of the blue node, which is this blue region. And then we have the star operator applied to this edge, which essentially is also the intersection of these 2 open sets I've just mentioned, and we get the open set in the middle. So we can see how the connectivity between nodes is essentially, we can express that topologically as intersecting open sets. So essentially we have this information that's localized. We have some features living on this graph on these open sets. And what we do when we perform message passing, essentially we kind of transform this topology of the graph into like a computational graph, right? So we make things communicate when different kinds of data overlap. So that's kind of the main idea. And what we're going to do is, building from this perspective, we'll just see how we can kind of get more interesting things. Okay, so the problems we're going to look at are 2 big and interesting problems in graph neural networks. And they all have to do something with node classification in particular. So again, just to kind of mention the setting we're going to talk about. So now we have only 1 graph. We don't talk about multiple graphs in this talk. And again, what we want to do is classify some nodes on this graph. And we have some labeled nodes, the red and the blue, and some unlabeled ones. And we want to label the unlabeled ones. So that's kind of the idea. OK, so first problem is what's called the over-smoothing problem, and Francesco will also talk about this. So the idea is that for some GNNs, and in particular graph convolutional networks, which we're going to see in a second, you can show that as you stack more layers, the features become smoother. So it's kind of the opposite of the big promise of deep learning, where we put more layers and things get more complicated. It's the other way around. We put more layers and things get less complicated, right? So like if features become very similar as we stack more layers, that's a problem because we can't separate the classes anymore, so we're in trouble. And this is a plot from a paper where they show how at each layer the features approach. So this is a distance from this subspace where the features are sort of constant, let's say, on each connected component. So this is kind of the sort of things we looked at in the previous talk as well. So basically everything becomes smoother. That's what that plot is meant to show. Now, another problem that we'll see sort of related is the heterophily problem. And here, this is kind of more universal. So the previous problem is more specific to certain architectures. But this one is a bit more universal, I would say, or it affects more models in general. So essentially, many GNNs, they tend to work well when your graph is what is called homophilic. So nodes that have the same label, they tend to be connected more than other kinds of combinations, right? And the opposite is heterophilic. So you have nodes with different labels, they tend to be connected. So basically, the sort of opposites attract is kind of the heterophilic setting. And Here in this plot, this is from a recent paper, this is the homophily level. So you see at low homophily, so high heterophily, so many opposites being connected essentially here, performance of graph convolutional networks is super low. As we increase homophily, performance gets better. And there's already some models that are kind of closing this gap, but it's still kind of an open problem in many ways, both empirically and how to kind of study it theoretically. And we're going to see one such theoretical way with practical implications in this talk. Okay, now let me show you something interesting about graph convolutional networks, and I think I was kind of alluding to that in my previous talk. So let's say we have a graph, a degree matrix, so that's just a diagonal matrix with the degrees of the nodes, adjacency matrix A, then we can define a normalized Laplacian operator, which is just identity minus the normalized adjacency, and we have the node features as usual. Now, if you could think of one simple process that suffers from both heterophily and oversmoothing, is heat diffusion. So that's kind of the anti-model, right? It's the worst sort of thing you could do, because if you've seen like some visualized at some point, it's just kind of temperatures become more uniform as time passes. So you can see that's pretty bad, because everything becomes uniform, everything kind of over smooths, right? And at the same time, if you have lots of connections between things you want to separate, those are the first things that you will smooth, right? So you'll make more similar things that are kind of different but connected, right? So immediately you make those things that you want to distinguish more similar. So you can see how both problems kind of are showing up in this process. And let's discretize this process and see something interesting. So if we just take the Euler discretization of this, we just get this simple equation, and we can just simplify it by using that these features are a common factor, and we get this expression in red. Now, let's look at graph convolutional networks. So this is the definition you see in the kind of GCN paper. So you have normalized adjacency as kind of your aggregation operator, your diffusion operator. You have some features, you have some weights, and some nonlinearity. Now, if you just look at the definition of the Laplacian, it's just a simple algebraic manipulation to see that we actually get the same red term there in this GCN. So in some sense, it's not surprising that GCN suffers a lot from these two problems, because it's actually built around this problem around this process that suffers from these problems, right? To some degree, maybe it's surprising that, okay, we've put some weight here and we put a sigma here, and that didn't fix anything, right? Like, we still have problems with this. So perhaps that's surprising, but to some degree, you could also see it as not surprising. So a natural question to ask is, how can we make this diffusion process more powerful? How can we augment it, make it more interesting? And then we can come back to this and say, okay, we have like some nicer equation here. Let's build another GCN with it, right? So that's kind of the main idea of this talk. Okay, and to do that, we're going to use sheaves. Now, I'm going to do something I've never done about sheaves, which kind of explain. So we work with these discrete sheaves on graphs. And these are some objects from quite complicated in some sense from algebraic topology and used in geometry. And often we kind of start with this discrete definition and say, yeah, this kind of like the simpler version of the continuous general one that mathematicians usually use. So I'm kind of trying to attempt to show you why these discrete sheaves we actually use in the paper, why they're actual sheaves. If you look at their definition, you'll see it's quite strange. So it doesn't actually look like a sheaf. And even experts, I think, are confused by this, like when they see that definition, because it doesn't look like a sheaf. So I'm going to explain why that is. Usually, there's lots of category theory showing this process, and this kind of advanced category theory. You have this theory of Kahn extensions. I don't fully understand, to be honest. So I'm not going to follow that approach. This is kind of a category-free approach to these things. But because Pim also conveniently introduced category theory, I'm also just going to mention verbally how various things translate in category theory. But you don't need to know any category theory for this. Okay, so here's the first thing. Obviously, before you go for drinks, you have pre-drinks. So it's the same here. Before sheaves, we need to have pre-sheaves. And here's what this pre-sheaf is. So basically, we just have a space, and we have some open sets on this space. And what we do is just we use some assignment of data to each of these open sets. So this notation is just the data assigned to this open set X, the data assigned to this open set U, and so on. And this data must follow certain kind of consistency checks. So in some senses, if I look at this data on this open set X, I can kind of see how that data restricts to a smaller region, right? So it's kind of, let's zoom in and see how this data looks on this smaller region, right? So that's the sort of thing we're doing. But there are multiple ways to kind of restrict, right? I can go this way and restrict to this and then to this, or maybe I can go directly and so on. And what he says is like these arrows should commute, right? It doesn't matter which way we go. We should always kind of, have this consistency. It doesn't matter in which way we zoom in. Maybe we look at this bigger thing and then at this smaller thing, or maybe we go via some other open set. We should always end up with the same kind of information. So that's kind of the idea. And what these arrows are just specifying are a way to restrict the data to a smaller region. So that's kind of the intuition. Okay. Now let's do the kind of formal definition of a pre-sheaf. And it's exactly what I've said, but just kind of a bit more formally. So for each open set in X, we just associate, I say here, a set. This could be anything. We're just going to use sets, but could be groups, could be modules, could be whatever your algebraic kind of object you like is. You could put anything there. And the elements of this thing are called sections, sections of F over U. Now, for each inclusion, so when we have an open set V that's included in a bigger one here, then we have this function that goes the other way around. So it goes from U, from this space F of U to this space F of V. And then, when we have like three things that are kind of included in each other, we need to have this kind of transitivity I was mentioning, right? So I can go like this, is the same as going as this. That's the only thing. Now, if you remember the category theory talk, this is essentially just a functor from the category of open sets. So you have open sets with, but now you have to take the reverse of inclusions and essentially to some other category. Here we use category of sets, but you could choose category of groups or whatever. So change that, okay? So that's all. It's just a functor essentially. So we just translate open sets and inclusion to these spaces and relations between these spaces. That's kind of the map. Okay, so let's look at examples. So we have the pre-sheaf of continuous functions over R. So essentially, we just say these spaces, so for F of U, we just have all the functions that are continuous on U. Okay, and the thing is, this pre-sheaf actually satisfies two nice additional properties. So the first property is called locality. So essentially, if you have an open cover for U, so that just means I have some open sets. When I take their union, they cover U. Their union is U, right? So if you see here, I have this blue open set, and it is the union of the green and the red one. So something like that, right? So what this says is some sort of uniqueness to decompose things. So it means if I have like this section, I can decompose it into these pieces. So I can take it into this function over the green part and this function over the red part. And that's unique, right? The only way I can get those splits is from that object. Like there's no other object that gives me these two functions, right? I think we can all agree that. So basically, I can't have another function here that gives me the exact same functions on these subsets, right? So that's locality. Now, there's a second property, and that's called that's called gluing. So again, this is kind of going in the reverse direction of what we've just seen. So again, we have some open cover for U. We have some sections on these smaller things. So just like some data from these smaller open sets that cover U. And now, if these things overlap, and they agree on their overlap, so here they agree on this overlap, these functions, it means there's a unique way in which we can glue this thing back, this blue function, right? So we can basically use smaller things to glue it back into bigger things. So that's the second property. And the first property implies this is unique. So actually, this is a redundant word here. Uniqueness is implied by the first property. Now, we've seen this example. Actually, this slide. Okay. Yeah, so what we can, I think there's a slide missing, but essentially what we can do, let me see what happened here. Yeah, I think there's a slide missing. Well, sorry about that. Oh yeah, no, I think it's fine. Okay, I think I just jumped too many. Okay. Okay, yeah, so we're here. And basically, to define sheaves, what we're going to do is let's first redefine some notation. So before, actually here, these functions, when we were kind of restricting, we were just kind of just taking the restriction of that function over a smaller set, right? So the way to kind of restrict this data to like some smaller region, we're just restricting that function to that smaller region, right? So nothing complicated. Now, what we can do is we can kind of reverse the notation a bit. So let's say we have some section, and then we have some smaller open set. Then let's just use this notation, this kind of restriction of function notation, to denote this kind of this arrow we were having in like the previous kind of a slide, right? So now when we have this map, we're just kind of denoted by that. And now a sheaf is just a pre-sheaf that satisfies locality and gluing. And just putting them here again, just to see like in these definitions, we haven't really talked about functions, right? Actually, if you look at these two definitions of locality and gluing, I guess the only way functions show up was in this notation for restricting. But if we just generalize this notation and say, you know, we will just use this notation for just passing our section through these maps that we have in the pre-sheaf, then we can just reuse this definition. So essentially, we can think of a sheaf as just a pre-sheaf that satisfies locality and gluing. And maybe one way to motivate this is Timothy Gowers, who's like this Fields medalist in Cambridge, had this nice blog post, like if you want to explain or understand certain things in mathematics, you could invent this alternative history, in like find a useful way to motivate something, right? And you could think of, well, functions, continuous functions behave like this, right? They have this locality and gluing, and then let's generalize this definition essentially, right? We just kind of, we'll actually call these things restriction maps, right? Just kind of motivated by this example and generalize this into other things because other things behave similarly. So that's kind of one way to motivate these sheaves. Okay, so we see that basically the pre-sheaf of these continuous functions over R is actually a sheaf because it satisfies locality and gluing. But there are other many things in topology, geometry, or whatever that satisfies this. So for instance, you could have a sheaf of vector fields over a smooth manifold. So basically, it's the same thing. Like if you have like two pieces and they overlap and the overlaps kind of agree, we can combine that in a bigger vector field. And one way I've put this is sheaves are about creating big data from small data. And this is a bit of a joke because I'm hoping if I put big data there, I raise the hype about sheaves. I guess the kind of nicer way to put it is like you get bigger data from smaller data. So you might still get some small data, but okay. So that's kind of the big picture. Now let's look at something that's a pre-sheaf, but is not sheaf because it's useful. And that's functions that are continuous and also bounded. So to see why these are not sheaves is like we can't glue these things and get other bounded functions. So they violate the gluing property essentially. So basically what you can do is you can take the real line and you can split it in like some unit intervals or something like that, like here. And we could put like, many of these to the right and to the left. Obviously, all these functions, you can take the identity, for instance, right? It's bounded on each of these open sets. So we take some sections, right? But when we try to glue them, we just get the identity over the whole real line, which is not bounded. So we violate the gluing property. So we get unbounding functions from bounding functions. So this is not a sheaf, it's just a pre-sheaf. Now, another example is the pre-sheaf of constant functions over R. So similarly, you just have a function that's constant over each year. Can anybody see why this is not a sheaf? Can you see how gluing constant functions can break things? Sorry? Yeah, so you can kind of get, I have a constant function here, constant here, but when I put them together, it's not constant, right? Because I have like not over the whole domain, right? So you can get locally constant functions if you glue them, right?
But if there are enough open subsets, probably you can glue.
Well, no, you get something like maybe I can draw here. So you can find examples where so you can have function like that, and this is here. And like in gluing, we just say, okay, if they agree on their overlap, now there's no overlap, so they agree, right? Trivially. But then if you look at this function, like the resulting one, right, is not constant. So that's kind of the idea. That's why this fails to be a sheaf. Yeah.
What about the units?
Yeah. So here, because you need to create other constant functions from constant functions, and that doesn't happen. So that.
Do you not have to assign one to every open set? Can you just pick like two disconnected ones?
Yeah. So if you look at the definition, it says for any open cover, so I can pick just this one, and it fails.
But if you included, like, you'd have to include a bit of that gap, and so they would have to, for them to agree, they would have to say on the overlap.
If your U is connected, then it's a sheaf, right?
Sorry.
If your U is connected, then it seems to me that must be a sheaf, right?
I'm not sure I understand your point.
Like if you took a real line of like with a gap in it, then you
Yeah.
could have separate ones. Whereas like if it's connected, then you have to include it. If like they'll only overlap if they're the same.
Yeah, I'm not sure. But like I'm pretty sure this is not a sheaf. So like if you just take R, you mean like taking something different from R, or like yeah. So maybe then yes, I haven't thought about it, but I just mean over R.
But if you mean all of R, then an open cover could be just like overlapping intervals, right?
Yeah.
But then they must agree on all these overlaps.
Yeah, no, so you'll find example where that happens, but it needs to hold everywhere and for any open set. So that's the point of this definition. So basically, it needs to happen. Okay. I can pick these open sets, right? You just need, you'll find somewhere, you're right, that doesn't happen, but it is like, it needs to kind of hold for any open set and any cover. So for any way to split your data into smaller things, this needs to hold, right? Because you might decide to split it like that in practice, and then this is going to break, right? It's hard to kind of say, okay, I'm just going to split it in this way. That's nice, right? So that's kind of the idea. Okay, hope that makes sense. Okay, so now we're going to work our way towards sheaves on graphs. So as I was mentioning before, essentially we have these open stars, and they form a basis for this topology. So we're just going to take this graph with the topology induced by the basis of open stars. So basically, all the open sets are what you see here, and unions of these things. And the approach we take here is actually inspired by this paper, A Brief Note of Sheaf Structure on posets. Actually, I've adapted some things from it, but it's very similar. So I think probably that's the friendliest one, but it's still not category theory free, and it still kind of has some, let's say pre-requirements, but I think it's much friendlier than other approaches. So yeah, have a look over that if something's maybe unclear from my talk. Okay, so here's what we're going to do. We can look at some things that are restricted just to this basis. So it's much easier to work with the basis of a topological space, and we have some notion of sheaves on this basis. But first, the pre-sheaf. So the definition is exactly the same, what we had before. It's just that now we just look at open sets in this basis. So we kind of ignore other open sets. It's literally the same definition. So for each basic set that we have in this basis, a set as usual, and for each pair, but again, this has to be member of the basis, we have a function. We call these restriction maps. Just kind of generalizing, as I said, the kind of restriction on functions with the usual properties. So again, you have to have that transitivity and composition of functions. That's nice. So again, in category theory, you actually would not have to make any changes. You just say, okay, I have a functor from this category of this basis, like just kind of restricted, because I think it's a subcategory of kind of the whole space. So it's the same definition categorically from category theory, but here I just said it again. Okay, now here we go. So first we have something that's a base pre-sheaf on the graph. So we could just pick all our open sets. We put like some set there. We have our restriction maps because this edge is included in both of these open sets. So then we must have these functions going to the set in the middle. So that's the key point here. Okay, now similarly to how we have these base pre-sheaves, we can also have base sheaves, which again is exactly the same definition. It's just that now we only look at these open sets in this basis. So we forget about other open sets. We just look at the ones in the basis. So again, locality, same definition as before. If we have two sections, the idea is that if we kind of split this open for any open set U, if we split it in like the elements of the cover, then and if we have basically these equalities, then we also need to make these sections, we need to have them equal. So essentially, again, you have a unique way to decompose things. And again, you have the gluing. So if you have this split of your data with agreement of the overlaps, we can glue them back together in a single thing. And now a little miracle happens. It turns out that any base pre-sheaf on a graph with the topology we use, given by the open set, is actually base sheaf. So it just trivially holds, like any pre-sheaf here is a sheaf. And the reason for that is because the topology is actually so simple that you kind of get that automatically and for free without having to do anything. So that's kind of one of the key ideas to prove these sort of things we try to do. So let's prove them. So let's look at locality and let's try, I've just put here exactly what we need to prove. Again, just so we have it in front of us. And the key thing in this proof is to notice, as I said, we need to look only at things in our base. In our bases, we don't need to look at other things. And we just have two types of open sets in our bases. So we have these kind of open stars around the node, and we have open stars around an edge, which is just kind of the edge itself, right? So let's look at this one, because it's very simple. Well, the only way you can cover this thing is by itself, right? It's just like a singleton set, that's all. And then it's trivial, right? Like if, look what we say here. So we have this S and T, and if they agree on UI, well, we only have, our only UI is this UE, right? So we have these things. This is by assumption, the thing in the middle. But UE is our entire set, so that's equal to S. This is our entire set, oops. So that's equal to T, so we trivially get that result, right? So for this second one, it's very trivial to show locality holds. It's actually not very hard to notice this also happens here by a similar idea. So actually to cover this point in the middle, the orange node, well, it's actually, it's big here just for visualization, but it's literally a point at the intersection of these things. To cover that point, the only way to do that, not because we only have these open sets, right? With these open sets, I can cover maybe these bits, but there's no other way to cover the point in the middle by actually including this thing. So any cover must have this thing in there. So we can also exploit that. So basically, for this UV, we notice that UV must be in our cover, right? The set itself must be in its cover. And again, a consequence of kind of the sort of topology we have on it. So yeah, because we cannot cover the vertex by other open sets, so we must include that. So again, similarly as before, we have by assumption the thing in the middle, but that's our whole set, so S equals T again. So it's kind of everything holds trivially just because of the simple topology. Okay. Now let's look at gluing. Again, I've just put it here so we can see it. Actually, the idea is the same, and we exploit the exact same fact. So let's look at this. So for UE, again, the proof is trivial. So we say we have two sections such that when they overlap, there's a unique way to glue them. Well, there's only like one open set here. So obviously this will be equal, right? The only intersection is the actual set itself. So obviously, and the only SI, there's only one SI. So you can think of like S1 equals S1 over UE, basically. So that trivially holds. Okay, now let's look at this kind of set again. And again, we use the fact that for some K in this index set for our cover, again, UV equals UK. So then we can just pick a section in UK, which is same as UV, right? Because these, oops, sorry. These are, whoa, why did it jump? Sorry. Okay, so we just pick a section, and now let's just check. So first, if we just restrict this to UI, we can just rewrite UI as UK intersected with UI, because remember, UK is the whole thing. So, if you just include the whole set, UI is same as UK intersected with UI, because UI is included in UK, right? So we got that. Now look at what our assumption is here. So we can replace this sk with si, right? The other thing that agrees on the overlap. So we have two sections, k and I, and they overlap. And this section must agree with the other section on the overlap. So we switch here from sk, we switch to si, okay? And now we have si, this is equal to uv intersected with ui because uk is uv, right? And we can rewrite this as si restricted to ui, and this is equal to si. Yeah.
So the graphs have loops or not?
No. Oh, they have loops. Yeah.
They can have loops.
Yeah.
And then two vertices may be connected by more than one edge.
We don't assume that here, but it should
Yeah,
still.
if you do such things, how can you be sure that you never get to this?
So here we don't assume any kind of strange. It's just like I don't assume self loops or any weird things.
I know, but how can you be sure when you glue things like that if you never get them?
Yeah. So I guess I dropped some information when doing this because I thought it was a bit tedious. But essentially, you have a partial order given by the incidence structure, and by using properties of partial orders, you can sure kind of by the axioms of partial order, you'll have situations like this. And basically that's all that happens. So you can, that's kind of the way to show, but I had to kind of to get rid of that to make things easier. So again, we saw like essentially just because all these covers all the time, they need to actually contain the set itself, automatically you get these conditions satisfied without any sort of work. Okay, so now we have a base sheaf on our graph. So we're approaching kind of the end of this. But then, you know, we still don't have a sheaf, so what's left to be done here? And if you're an algebraic geometer, there's actually very nice result about this. It turns out that sheaves are a bit like linear operators. So when you have a linear operator, you just specify how it acts on, you know, each element of the basis, and that defines the operator completely. It's the same thing here. If we have a base sheaf, we can canonically extend that into a sheaf, right? We kind of specified everything that's needed to construct a sheaf. We don't need to do anything more. So basically, our work stops here. We are done. So this is the theorem, and this is kind of probably in the first chapter on any kind of sheaf theory book. And essentially just says if we have a base sheaf on a space X, it uniquely induces an actual sheaf. So this is a base sheaf, but it induces an actual sheaf. And I use this F plus here on X such that F and F plus are canonically isomorphic. What canonically isomorphic means here is just that essentially they encode the same information. So any information encoded in F plus, I can sort of map it back to some information in F. So we don't lose any information. So you could think of the base sheaf as kind of a compressed representation of the actual sheaf, but it's a lossless, yeah, a compression without loss. So it preserves information. Okay.
No, don't write this. You don't need it.
Well, I think it gives a nice. So I just wanna say how this sheaf F plus looks like, and it's actually quite simple. So essentially, if you have an open set U, that's what we need to do. Like we need now. Okay, tell me how these spaces F at, you know, how the data attached to every open set. How does it look like on this sheaf? So it looks like this. Like if we have some open set, what we do, we look at all the base open sets that are included in that one. So for any open set, right, we're just going to have these smaller ones in the base, and we're just going to look at all of these and pick some data from each of these. So this SV will just be a sequence or a tuple. Essentially, just enumerate all your open sets from the base in that open set. Essentially, just enumerate them, pick some section from all of them, but you also have to satisfy a condition. You need to make sure these restrictions hold, right? You need to make sure that this is true. So let me give you an example. And this is kind of the core idea of what we're going to do next. So essentially, here, this is a very simple graph, right? We just have like 3 open sets in our bases, again, orange, blue, and the intersection, okay? So if we want to assign the data for the whole open set, so their union, all we have to do is go over all the base sets in this. So we have these 3, right? And we just go over them and pick some section, right? We have S at UV, so some point in UV, S at UE, some point in here, and another point in U, right? So that's all. We have these tuples. So just go over all these base components, pick a point from all of them, but they also need to satisfy these constraints I was mentioning, right? So if we have a point here and we restrict it to here, and another point here that we restricted to here, they all need to agree and they need to be equal there. So that's kind of the idea, right? You see the orange and the blue, they overlap, and also the point UE, the section we pick in UE is exactly that point as well. So that's the idea, right? When we map things from here to here and from here to here, these must agree. So that's kind of how we construct these bigger things. And now if you want to also see how the restriction maps look like, it's very easy. So if you restrict to some smaller open set, so let's say we drop the blue one, well, you just drop these things from these tuples, right? You just consider smaller tuples. Obviously, if you're kind of if these equations are respected over this bigger region, they're also going to be respective over a smaller region because we just drop constraints if we look at a smaller region. So that's the idea. So we call these sections over some other bigger parts of the graph, essentially. Okay, so that's the idea. Now, normally I would start the talk here, and now hopefully this motivates this kind of a definition that we use here. So these are some objects that were kind of introduced formally in Shepard's thesis in '85, and there's also a funny story about that kind of got lost, and then this PhD student of Robert Greist kind of brought them back in the applied domain and kind of formulated them more nicely, and then there's been lots of nice work from that group kind of making them applicable in practice. But essentially, what these cellular sheaves are just these base sheaves that are actual sheaves, as we just proved. There's just some tiny kind of aesthetic differences. So now we kind of drop all these open sets because notice before we just had the open star, but the open star is associated with that vertex. So we can just imagine putting the data at that vertex because it's much easier to talk about, combinatorially about vertices, edges rather than these open sets. So this is where these kind of, well, that's the main difference. And now we're also going to talk about cellular sheaves of vector spaces. So far we just said sets because I tried to be kind of general, but like it could be anything. Again, this will be just a functor to some category, and here's the category of vector spaces. It could be other categories and so on. And obviously for machine learning, vector spaces are great because that's what we do. So we use that. Okay, so here's the definition of this thing. And everything we've done so far was just a way to motivate this definition and to see why these things, they're actually sheaves, right? So if you actually, after you see this definition, you'll see that, where's the locality, where's the gluing? You haven't said anything about that. So, why are these actual sheaves? So that's the idea. Okay, so we have a vector space, essentially f of v for each v. We have a vector space f of v for each e. So as before, kind of for each open set, we had one of these spaces. And again, going from v to e, you have these restriction maps. So these are just linear maps in this case for each vertex incident to an edge. So that's pretty much everything. And again, might be weird, like why do we call these restriction maps? Now it should be kind of clear. But on the graph, might look strange to call those maps. But now that you see where they come from, maybe it makes more sense. Anyway, so also some terminology. We call these vector spaces. In this case, we call them stocks. And yeah, as I said, the linear maps are called restriction maps. So there's just some terminology because it might show up. Okay. Now a nice mental. Yeah.
But stocks have a meaning for sheaves.
Yeah.
These are not the stocks.
They are actually. So.
Because it's only finite topology. So when you do the stocks, will be the intersection, right?
Yeah.
And if you dissect, you're not gonna get ever E, are you?
So you can show, so in this paper I linked before, for instance.
FE maybe, FE, not FG, right?
So when you kind of consider the kind of the partial order set approach, there you could put the topology on the partial order set, and then there you see that basically this will correspond to what in Sheaf theory are called stocks. But again, I don't want to go into that because there's more.
Question FV. FE, it's okay. FV.
Right.
FV is a stock?
Yeah, so I think yeah. So you can also show like via category theory, just kind of other approaches that it is actually a stock. So it's kind of because I think it's because the smallest open set containing V is actually the star. So that's
right.
Yeah.
That's not open.
No, it is an open set.
V is open?
No. I mean the star.
So as you said, the stock is obtained, by taking the intersection, and you can never get V as that. That's the thing. That's what confuses me. V you can. V you cannot.
Well, but like V is not in kind of any intersections because like other things around it, like they don't include V. So essentially, it's kind of you kind of get it like in a kind of vacuous way, I believe, sort of thing.
Right.
Yeah.
I'll get to the paper.
Yeah. I think probably the paper I linked in a few slides, probably it's the most illuminating one. But I think that's the stock thing is an actual terminology from Sheaf theory for context, but it's not really important. Like just take it as it is, right? For this thing. Okay. Now there's a very nice mental kind of picture you can have of these objects, and this is due to this paper by Hansen and Grice. Where they use these things to kind of for opinion dynamics, and it gives a very nice interpretation of these things. So you could think of the vector spaces of the nodes as a space of private opinions, and the vector space of the edges is kind of like a discourse space where kind of these people, so if the nodes are people, they communicate in that discourse space. And what these linear maps are doing, they kind of transform a private opinion into a public opinion, right? So we just say, how does my private opinion manifest in public? And fortunately, we don't always say in public what we actually think. So that's kind of the way to model that, right? You have this filtering of opinions that's done by the linear maps. And I should have also said that because we said these are linear maps, there's also like a canonical way to go the other way around by just taking the transpose of these matrices if we represent these things as matrices. And we can also move the other way around compared to kind of the arrows we saw in the Sheaf kind of introduction. Okay, so that's one way to think about these things. Is my battery gone? Okay, no, it's still alive. Okay, cool. So let's now start using this and actually do some machine learning with this. Okay, so we can have this space, what's called of cochains. So essentially, you just take all the vector spaces of all the nodes and you put them together in a bigger vector space. That's all right. We want to talk about all these vector spaces of the nodes in like a single object. And this is called the space of zero cochains. So just basically direct sum of all these vector spaces. We can do the same for all the edges. We have another direct sum. These are a space of one cochains because edges are one-dimensional and so on. So this just gathers all the stocks in a single vector space. Okay, so once we have that, there's a very natural operator we can define going from this space of zero cochains to the space of one cochains. And for that, we also need to pick an orientation for each edge, and it does this. So let me explain what's going on. So maybe one thing that you might be familiar with is kind of like a gradient operator. So actually the boundary operator we talked in the previous lecture, if you take its transpose, it actually does what you see here. So essentially it behaves like a gradient. So if you have some scalar signal for each node, when you take this gradient, you'll get the difference of these scalars. Okay, so that's what's going on. And this is the sort of thing, the sort of operator we looked at before. It's just kind of a reverse way to look at it. And what this is doing is kind of generalizing this thing to kind of vector fields. So now at each node, we're just going to have this vector that comes from the vector space at that node, and another one for the other node. And this is kind of like what we have like with the covariant derivative in differential geometry, like a way to differentiate vector fields. So that would be, let's say, the geometric intuition, but I guess this is a bit more general. So if you want to compare two vectors in different vector spaces, you need to bring them in a common vector space where you can kind of compare them, right? So you use the discourse space, the thing in the middle, as a space where these two things meet, and then they can be compared, right? So what we do is, we take the first vector, we pass it through some matrix, we take the other vector, we pass it through some matrix, and take the difference of these things. And that's just a way to kind of like a discrete differentiation of vector fields if you want, if you like the geometric intuition. And the thing I want you to notice is that this is just a more general version of the thing on the left. So actually we can recover the thing on the left from the thing on the right. So if our vector fields are essentially scalar fields, right? So we just restrict to scalars, we just have scalar functions. Now assume we just make these matrices the identity, right? So we just get exactly what's on the left. So in some sense, it's a way, with the sheaf, we have a way to put like a more complex geometry on the graph. That's, let's say, the geometric picture, but it's more general than that. Okay, so in the previous talk, we saw this sort of picture that we call these chain complexes where we have boundary operators going that way. Now, what we could have done, and there were some reasons I kind of chose the first one for kind of educational purposes, but there's kind of a dual picture. So we could have just took the transpose of the boundary operator, like informally speaking, and then you could go the other way around, right? So like instead of just taking these boundaries, you would have these things called co-boundaries that go the other way around. And if we did that, we would have obtain what's called the cohomology group, which is just the cousin of homology. So, and actually, this cohomology group is isomorphic to the homology group as vector spaces. So essentially, it's just a different way to talk about these holes we saw in the first part. We just go in the other direction. And this is kind of more like if you're familiar with this exterior calculus, this is kind of like discrete exterior calculus. So that's, but if you don't know what that means, it doesn't matter. We don't need it, but just in case you're familiar. Okay, so, sorry, there's some delay in. Okay, so the thing to notice now is that we have one of these co-chain complexes, but it's just like a very short one because we just have vertices and edges and then nothing else, so we just stop there, right? And our coboundary operator is just kind of the first operator in this chain, but you can actually, cellular sheaves are called cellular sheaves because more generally they're defined on cell complexes. Here we look just at graphs, but so we stop there, but if you have a bigger cell complex, you can kind of keep going. So we can define the zeroth sheaf cohomology group in the same way. So it's just the same definition we had before, essentially. So so here we just have kernel of this coboundary quotient delta minus 1. This delta minus 1 is just 0. Sorry, yeah, it's just we can get rid of it essentially. So what's the point of this? What are we kind of trying to achieve with this? So before we just had this zero cohomology group that was about connected components. So that was kind of the main thing. And that's boring, as we were kind of arguing, right? You get these very smooth signals if you use that. It's very boring. You can't do something useful with it. But now that we put this shift structure, we get a new cohomology group that's much more complex, as we're going to see. And then we can use this to define a diffusion process that's much more complicated. So that's kind of the idea. Okay, so now that we have this coboundary operator, we can define a Laplacian operator. So if you actually look at this coboundary as some sort of gradient, or as I was kind of, or covariant derivative, you kind of get this, the continuous definition of the Laplacian as divergence of the gradient. So this is something like that, but it's generalized to these sheaves. And what it's sort of doing is kind of like an aggregated way to measure disagreement across your network. So essentially, at a certain vertex v, if you evaluate the output, what you're going to see is you just have the kind of difference in opinions in the public space at all the edges incident to that node v. And then you map those back at the node in a signal over the node. Okay, so how does this look like? Kind of, it's just a matrix, and it's a block matrix. Your kind of diagonal entries look like this. Non-diagonal entries look like this. And if you look at kind of, I think the non-diagonal entries are kind of a bit more important here to notice the intuition. This is just a way to move like a vector from one vector space to another, from like a neighbor to another. So it's just a way to move vectors from like a neighbor to my vector space, right? So if I'm a node, this is just a way to express, give me all the, move all the vectors from my neighbors in my space and then aggregate them. So that's kind of what this is doing, right? And here, just to see like how we use this. This is just one of these zero co-chains. So essentially, we just stack all the vectors from all these sections, right? So we just stack them in a single vector, and then this is compatible with the Laplacian, and we can just multiply. So that's kind of the how you implement these things. Now, what is important to mention here is that we also have a normalized version of the Laplacian. So what you do, you just take all these diagonal blocks here, and that gives you another matrix, this D, and then we can normalize this how we also normalize any Laplacian, right? We just use the symmetric normalization. I should also mention here that we assume all the stocks have dimension D, and these blocks, because of that, are D by D. In general, you don't have to assume that. So you could have vector spaces of different dimensions at each node, but we use that just for simplicity, and it's sufficient. And again, to notice what I was saying before, if we just make D1 and these matrices to be just identity, again, we just get the kind of the gradient and divergence, like the regular ones, the simple ones for scalars, and then we just recover the graph Laplacian. So this is kind of a way to generalize the Laplacian to vector fields and even tensor fields and things like that. So you can do much more complicated things. Okay. Now,
sorry.
Yeah.
In case of the Sheaf Laplacian, we don't have symmetry. It's not a symmetric map.
It is. So it is like a positive semi-definite operator. So to notice that is just from this expression here. Everything that kind of looks like that is positive semi-definite. And it's symmetric. Yeah. Okay, so now something very cool happens. So the sheaves with orthogonal restriction maps, we call them discrete OD bundles. So why is that? So essentially, you could think of these stocks we were mentioning as a tangent space to manifold. So like if your graph, sort of imagine it lives on a manifold or something, you saw like in Maurice's talk how we can do parallel transport to move these vectors from one vector space to another. Now you could think of these multiplications that we were doing to move a vector space to another vector space as a discrete version of parallel transport. And I think the main thing I want to say here is we should just appreciate for a second how we got geometric structure on the graph without any sort of assumptions. Like we don't assume this is a manifold or anything. We don't assume the graph comes from a manifold. We haven't done anything weird. We haven't guessed. We just said we start from topological spaces and we end up with a discrete vector bundle. So that's a very nice bottom-up way to recover geometric information on the graph without doing anything. And we not just only recover geometric information, we have more than that, because this bundle setting, we assume these things are orthogonal, but actually in general, they don't have to be, and you could have very weird maps there. And if you actually use the full power of category theory, these things could be other, not even linear maps, could be like much more weird objects. But you would also have to find some applications for that. Okay, so that's the analogy here. Okay, but mostly I think we're going to work to some degree mostly with these bundles. Okay, so let's get to the machine learning part. So now we can just consider a diffusion equation on this sheaf, and algebraically it looks exactly the same like what we had before, right? The same kind of equation. All that changed is just this subscript. We just have this delta F because that's just to denote we have another Laplacian here, and that's the Sheaf Laplacian. And what we can do, we can also use a feature matrix. So if you have multiple feature channels, we can just stack that way multiple cochains. So each column is one zero cochain, and we have multiple of these. So you could think for each of these rows, like block rows, corresponds to like multiple features from the stock of that node. So all we have to do is multiply this block matrix by this sort of matrix. And we can actually say something very interesting already about how this works. And we actually saw this before. It's just restating this in terms of sheaves. So if we do this kind of diffusion process, we just converge in the infinite time limit in the kernel of this Laplacian, which is isomorphic with this cohomology group. So basically now we have a much more interesting cohomology group that defines this or the asymptotic behavior of this diffusion process. So now we can converge to things that are not necessarily constant on each connected component, like we saw with the GCN. We can actually do much more complicated things. Okay, so that's the idea.
Chris,
yeah.
Sorry, just question/comment. So can you give an illustration for the opinion dynamics for the difference between the dimension and the number of channels?
Yeah, sure. So So yeah, I'll also mention that a bit later, but essentially you could think of D as kind of like, you know, the dimension of your manifold, I guess, in some sense. And the feature channels is kind of having, so if you think like each column as a vector field, the feature channel is kind of like having multiple vector fields on your manifold, right? So like, imagine you have multiple vector fields, so you kind of have multiple copies of that. So that would be kind of the intuition, like geometric intuition. In terms of opinion dynamics, I'm not sure exactly like what you could think of like one instance of basically one column, I guess. Like these are private opinions about some topics. So each scalar in here is kind of like a scalar opinion about some topic, right? So if we, let's say, talk about football or something in the first scalar, I can have like a very positive opinion or like some very negative opinion of football. Or if we have like a scalar about topology here, you know, we can have a positive opinion about topology or a very negative one. So we can have like each dimension in that vector is kind of a topic, right? And when we map them through like the linear maps of the restriction maps, one of these is kind of like maybe the opinions about other topics, which might be linear combinations of your private opinions about these topics, right? So in the public discourse space, you have other, and you could think of each kind of column as kind of an instance of that, right? So you kind of have potentially other topics you can kind of think about. So that's kind of the intuition, I think. Okay, so what we want to say is like, we want to look at what classes of sheaves can linearly separate the nodes of a graph in the infinite time limit of this diffusion process. So here's essentially an example of that. So we start with this graph on the left, and the positions of these nodes are essentially the features. So that's kind of the way we visualize the features. There, basically every node is embedded somewhere in this plane. And you can see all these classes are so entangled, it's very hard to separate them. So even like with like some, you know, like nonlinear decision boundaries or whatever, but we want to find a sheaf such that when we run this diffusion, and this is actually coming from a real sheaf on this, look how everything becomes, sorry, everything becomes very clustered and nicely separable at the end. So in the last picture, we can just draw some lines and visually separate all the classes. Yes?
So what are the restriction maps?
So they'll just be matrices, and I'm going to give some example, but like I'm going to get to that. Okay. Cool. So what we need to understand before we do that, we need to understand the properties of this kernel. In particular, a good question to ask is, when is this kernel 0, right? So 0 is like it just has the 0 element essentially. So basically, why we want to avoid that, right? Like if we just have 0, all these things will converge to 0 in a single point. We haven't achieved anything, right? Because like everything's in a single point, and we can't separate anything. So that's boring, and we certainly don't want that to happen. So first, what we do is analyze the harmonic space of the Sheaf Laplacian in the bundle case, because it's easier to do it there. Okay, and turns out that's sufficient. So if we have a bundle, we can have like any path between two nodes, right? And what we could do is consider this notion of transport from one stock at node V to the stock at node U. So kind of transporting these vectors on longer distances, essentially. That's all we're doing, right? So far, we only transported like one hop away, but we can go like multiple hops away. And that's very easy to do. You just kind of, you know, compose these matrices along all the edges between those nodes, picking some path. Okay, and the main idea is that the harmonic space of the Laplacian, or of this kind of bundle case Laplacian, it's also called the connection Laplacian, is related to the path independence of this transport. So that kind of determines if this kernel is 0 or not. And I should say that basically all the proofs in this section were done by Francesco. So, you know, if you have like more advanced questions, ask Francesco about this. Yeah, so basically here are some inequalities kind of Francesco proved. So if we have these bundles, then for instance, one way to measure this kind of path independence. So also I should mention in the geometric setting, as you also saw in kind of the talk from Maurice, if you like actually have curvature on your surface, like you won't get path independence. So here, like if we start with this vector, we move it here and then here, and come back, we see we get a different vector, right? And that's not like path independence, because we could have taken the trivial path, which is just stay there, basically, don't move. So that's kind of a trivial path, and this other path gave us something else, so it's not path independent. But what we can do is like compare all your kind of paths between two nodes and see kind of what's the maximum difference between them, between all these paths, and then just label these as R, and then we can show that the eigengap, so basically the zero eigenvalue of the Sheaf Laplacian is bounded above by this thing, right? So that's an upper bound. And then there's also like a lower bound. So again, you can frame these in terms of cycles, like here. So we can kind of measure what's kind of the deviation from, like, let's say you just stay here, right? Or you move around in a loop and you get something else. So what's kind of the sort of deviation we get there. So that's kind of the idea here. And this is kind of, this epsilon is kind of measuring that sort of deviation you have. And then you can show that this lambda 0 is lower bounded by this times some constant that depends on the graph structure, so the kind of graph diameter and other things like that, degrees, but it's not important. Anyway, so what's kind of the takeaway from this result? So if the transport is path independent, then notice that both R and epsilon are 0, so we have delta 0 equals 0. This means that there's at least one harmonic eigenvector, so the kernel is not empty, right? We have some interesting things in the kernel. So that's all this says. So essentially, this gives us a recipe to how do we find some interesting kernels so we can kind of design some nice diffusion processes. So that's the intuition. So we're doing exactly that. So first, let's consider a very simple type of class of sheaves. So we'll just say we'll make these restriction maps to be equal along all the edges. And you can actually show, so there's a proof in our paper, that this gives you weighted graph Laplacians. So in a weighted graph Laplacian, all you have is like a positive weight for each edge. You can think of it like some similarity or something between the nodes. So you just have these weighted edges, right? So it's a slightly more complicated Laplacian than the graph Laplacian. And you might wonder, okay, maybe if we just do like heat diffusion on this kind of weighted graph, maybe heat diffusion is not that bad there, right? Because we made it a bit more general. We don't just have the usual Laplacian. Maybe all those weights help with something, right? And to some degree, it does decently in certain settings, but it must be like some sort of homophilic settings, or at least that's for what we prove this result. So basically, imagine you have a class of connected graphs with two classes. So now we just do binary classification. And we assume that in one of these classes, for every node, there's another node in its neighborhood that's also in the same class, right? So if I'm a node, I look around and I find another node that looks like me. That's the idea. It's not a strong homophily assumption, right? Because you can have like 1,000 neighbors that don't look like you and just one that looks like you. So it's not like super homophilic, but it's kind of like a minimal sort of assumption. But it's in some sense weak, right? And even in types of these kind of metrics for measuring heterophily or homophily, your homophily can kind of go to 0 if you kind of increase all these neighbors that are not like you. But you have positive homophily essentially. So you can show for this type of things that this class has linear separation over these graphs. So what does that mean? It means if you give me a graph with its labels from this class, I'll find your sheaf, I run diffusion, I separate the classes. So that's for almost any initial conditions. So in the dense kind of sense. So, okay. Now here's something where this doesn't really work anymore. So like if we have a bipartite graph, again, where the partitions are the two classes, then what happens is that if these partitions are equal actually, so this is the maximum heterophily setting, everyone looks different from me, right? Well, everyone, because I'm connected only to things in the other partition and those have a different label. Then if you run diffusion with any sheaf in this class, you will not be able to separate perfectly. So you can't have 100% accuracy essentially basically for any initial conditions. So whatever initial conditions you pick, or like basically features at the beginning, you can't separate these things. And actually, it's even, I think it's even stronger than linearity here. It's just you can't separate some things because they will have the same representation. Okay. So let's fix these things. And obviously the way to do that is just consider, drop requirements, because we put some kind of constraints on these sheaves. So let's, get rid of that. So let's look at some class of sheaves where that break that constraint. So imagine this. So for each edge, right, pick the first matrix. So remember, we're still in the scalar case. So all the stocks are just the real line. So single dimension. We don't do higher dimensional stuff yet. So for the first one, pick this matrix, which is a 1-by-1 matrix. Essentially, it's a scalar, right? Pick it to be minus alpha E, where alpha E is positive, if V belongs in class A, and pick it to be alpha E if it belongs in the other class. Okay, so we get this sort of things like here. So we have a minus something like, so here I just picked alpha E to be 1. So let's just assume it's 1. It doesn't really matter. So pick a -1 on one side, you have a 1 on the other side. Now let's look how we can actually, if you are to get a section over this, so remember when we were looking at kind of the more general definition, sections are just all these vectors that agree essentially globally on that section, essentially. So the only way for these two private opinions to agree is for one to be negative and one to be positive, because we multiply by -1. So notice, like, this is negative, and multiply by -1, we get a positive opinion. So that's the only way for these two individuals to agree. And then diffusion, it will force our process, it will force our features to be negative for one class, to be positive for the other class, and it's trivially separable, right? Like, just compare with 0. Is it smaller or bigger than 0? And that's what gives you the class. So that's the intuition, and actually you don't necessarily need this negative positive. For instance, if you don't use normalization, so like for instance, if you use just a regular Sheaf Laplacian without normalization, you can even find other kinds of easier ways without even using the signatures. But in the normalization case, that's kind of needed. Okay, so the result from this is that basically for any connected graph, we don't assume anything, could be heterophilic, homophilic, whatever. It just has to be connected essentially. This type of sheaf can separate the classes of any such graph for almost any initial conditions, essentially. So basically just pick this sheaf over your graph, but that assumes you know the labels, so that's important. But so that's kind of where the practical problems come. But notice that for the previous type of diffusion, even if we knew the labels, we still can't do anything, right? There's kind of an upper bound to what we can do. Okay. So first, let's kind of remark something that in this dimension, even with this extra generality, we still have some troubles. So like if we want to increase the number of classes, so far we've just done binary classification, then if we just keep like working dimension 1, no sheaf can separate the classes for any initial conditions. And the intention for that is that the kernel is one-dimensional, so you're just going to project things on a line. In the happiest case, you end up with something like this. Here we take for like linear separability like a 1 versus all approach. So basically you can draw a line and separate for all the classes. So for the blue class, you would need kind of two hyperplanes, one here and one here. Now you can still do that with like kind of some linear decision boundaries if you use this notion of pairwise linear separability. So basically if you just take any two classes here, you can always separate them linearly, but you cannot separate a class from all the others with a single decision boundary. So essentially you would have to do more work, which is kind of quadratic in the number of classes if you actually want to separate these with linear decision boundaries. So anyways, by linear separability here, I just mean like 1 versus all. So basically having a single line that separates you from all the other classes. So you can't do that here. So obviously, again, what's the solution? Well, we just eliminate that restriction. We go in higher dimensions. So this is kind of the equivalent of considering manifolds with higher dimension. In some sense, like if you think of like the geometric picture or like bundles with higher dimensional vector spaces. Okay, so what we can do is like the next simplest thing we can do is just make these matrices to be invertible and diagonal. So that's very simple, and all the stocks are RD. Yeah.
Sorry, so is it dimensions for the edges or for the vertices? Because for the vertices, dimension is fixed depending on the data that's provided.
Yes.
Increase the dimensionality of the data functions.
So what do you mean? I'm not sure.
So basically, what allows you to go to higher dimensional stocks?
I see. So the question was like, what allows you to go to higher dimensional stocks? Well, like there's nothing like in this kind of formalism that stops you from that. So it's kind of like you just have a vector bundle essentially. So imagine you can just tag vector spaces on top of something. You can make those vector spaces as big as you like, basically, in some sense. So that's kind of the intuition here.
What I'm saying is different. So let's say that I give you a graph, right? So
Yeah.
input to your classification problem is a graph with d-dimensional features.
Yeah.
In the nodes, right? So or d channels, right? So basically, what allows you to increase the dimension?
All right, I see. Okay, so the question is like basically we might get some. Usually we don't have vector field features. Yeah, like we just get like some random numbers that mean various things, right? In practice, so that's something I'm going to get to a bit later, but I can anticipate that a bit. So we don't restrict that your features initially are exactly like this, like d-dimension or something, because that's never going to be the case in practice or very often. You just have some extra features, like if you work on a social network, what's a vector field on a social network? We don't have something like that. You just have some stuff like, gender of the user or something like that. But what we do, like in the beginning, you can reshape your features in a way that looks like a vector field, and that's what we do in practice, and that allows us to use this formalism anywhere. We don't need to have like strong requirements on the input. Yeah, that's a good point. Yeah. So it's more like how we encode our kind of features before we do diffusion, right? It's just something we can fix with encoding easily. Okay. So what we can do with these diagonal restriction maps and the intuition behind this proof. So essentially, if this dimension is at least the number of classes, then again, we can linearly separate anything for any sort of graph. And the intuition behind this is that we can take some of these kind of scalar diffusion processes that we saw before, and we can kind of encode these in kind of the diagonals of this. So it's kind of like doing multiple diffusion processes in parallel, so kind of just scaling up the previous idea, the -1, kind of proof that you saw, and you can just scale that up by kind of encoding multiple diffusion processes in kind of a single diffusion process with these diagonal matrices, and that's the kind of idea to prove that. So it's kind of a very easy idea. Okay, now, you might say that diagonal restriction maps, they are quite simple, so can we also do better? Yeah, we can just look at these bundles that we've been discussing, and essentially here what we proved that for dimensions 2 and 4, you can classify 2 times that many classes. So basically if you're in dimension 4, you can classify up to 8 classes. Now, before anyone asks, like why in dimension 2 and 4, because I'm sure you're asking, is because like kind of generalizing this is kind of, I don't know, if I found it difficult at least, and I'm not sure if it actually holds. I was pretty convinced it holds only in these dimensions, but I'm not sure. So yeah, basically it's just something that, we have a proof for these dimensions, but in general, like the idea is you can essentially make better use of your space to classify more classes by using more kind of complicated maps. And I guess to some degree, I expect or like conjecture that you in general, you'll have some extra advantage by using more complicated maps and make more useful use of the space. It might not be 2 times d, it might be 1.37 or something like that. But you might take have some advantage from that, or at least that's my intuition. Okay, and here's another diffusion process on one of these bundles. Actually, the previous one you saw was also on these bundles. So again, this is just to kind of prove this for dimension 2, right? We have 4 classes, we're in 2D, we end up with this kind of very nice shape, and we can separate everything. Okay. So what's the kind of main takeaway? So like just to pause for a second. So, if you like have fallen asleep for the past 15 slides or something, then the takeaway is this. Basically, different classes of sheaves induce different diffusion processes with different capabilities. So we can have that flexibility by playing with this structure. We can play with these diffusion processes. We can play the cohomology group. We can play with the asymptotic behavior of these PDEs. We can make kind of classification much easier in this way. And the big point, I think, is this. So this is kind of summarizing all these theoretical results you've seen. If you want to do a node classification problem on a connected graph, you can always solve it by doing using Sheaf diffusion. So that's a very powerful tool. So it kind of justifies the use of these things to solve node classification problems. So essentially, we can always find a sheaf that solves our problem, at least in theory. In practice, it's not easy to do that. And that's what we're looking at next. So obviously, the problem is who gives me these sheaves, right? Like we don't have the labels. We don't have all the labels. So in this result, we were assuming we have the labels and we need to construct a sheaf. But in practice, you have some of the labels and you have some features. So you want to kind of generalize, okay, what sort of restriction maps should I put, at the places where I don't have labels, or for the, around the nodes where I don't have labels, so I can perform classification nicely. But at least it tells us there is a solution, right? There is something we could, in principle have, whereas for certain types of diffusions, there's no chance, right? Like even if you have like something super perfect, there's no chance you'll find something. So at least we have a chance, right? That's all these results say. In practice, we have a chance to solve the problem, whereas for these some things we don't have a chance, like at least not perfectly. Okay, so what we do is let's learn these restriction maps and use deep learning and the usual story. Okay, so what we are doing essentially, we have a parametric map which is matrix valued. So what we do essentially, we take the feature of this node V. So you'll have some features at the beginning, like for all the nodes. Take that feature, take the feature of the other node, pass them through these functions, which was also shown in red here. These will give you this matrix, right? And to get the other matrix, you do the same, but you supply the features in the reverse order. So that's all you do. So first supply this feature, and then this other feature. And then you get this other matrix. And you kind of go with this function, you go over all the edges of the graph, and you fill in these matrices. That's, yeah, question. You asked like how do you pick a basis for these things? Yeah, so we just kind of work in the standard basis, so it's not like we don't. So you'll just get the matrix and that's all. Yeah, so imagine like you just have a matrix essentially here, and this function will give you the number of that matrix basically, and then you can use that. So that, yeah, but like you can play a bit more with like, first you could put like inner products here and do like more interesting things, I guess. And actually, as a side fact, when you normalize a Laplacian, this normalization can be, so this is something related to what Pim was asking, that you can interpret that as some sort of weighting for your of your sheaf structure that gives you that kind of normalized Laplacian. So the normalized Laplacian is kind of the Laplacian of a certain sheaf that you've done some manipulations to. So the perspective that was kind of the matrix perspective I gave you was slightly, more like kind of matrix oriented. But anyways, so coming back to these points, we have these matrices now, and now that's all we had to do. Like that's our sheaf, right? Because for these talks, we don't have to do anything. I mean, you have to pick some dimension beforehand. Like here's 2D, right? These boxes are meant to show 2D, but yeah, other than that, you don't have to do anything. Just have these matrices. Once you have these matrices, you build a Laplacian, you can normalize, you have everything. So that's the idea. And the thing I want to point out is that actually this uses a very small number of additional parameters. You just have, this could be like a linear layer, for instance, or a multi-linear perceptron, MLP, like, yeah. So you have all these choices, right? Like, and that's all the parameters, but these are shared, right? You use the same parameters to compute these over all the edges. So it's very like low number of extra parameters. And one way I kind of found to explain this recently is you could think of this as a generalization of GAT. So in GAT, you learn some attention coefficients by this function. So it gives you a scalar. Here, we learn something much more general. We learn a matrix. So we learn a more complex way to transform our inputs, essentially, than just a scalar multiplication that GAT gives you. So you could think of it like that. Okay, now once we have this, yeah, sure.
So in a way, can you go back to the previous step?
Yeah.
You're taking the two inputs as an input, and then you're applying that again to one of the inputs.
Yeah, it's very recursive, yeah.
Is there a reason why you wouldn't just take the two inputs and output the direct output without explicitly having this matrix vector product, and then maybe just have a separate neural network to model the transpose thereof? Do you really need them to be transposed?
Yeah, let's write a paper. Yeah, no, I think it's a good point. Yeah, I think you could do that. I think maybe I think probably something this gives is like some sort of interpretability. And I guess you still want to, if you kind of go in that direct way, I guess you still want to make sure it can be formulated as such, I guess, if you want to keep that formalism. So like you can't just pass it through like any, because in the end, you'll just do like a matrix vector multiplication, right? So you still need to do something like that in the end. So yeah,
but it isn't really linear anyway, so. Yeah,
well, yeah. That's true, but you still have like some matrix that's a nonlinear function of your inputs, and then so you have some restriction there, I guess, to some degree. So yeah, I guess you would have to be careful to make sure what you do is still equivalent to this in some sense, or at least.
Does your theory kind of meet those restrictions?
So if you actually, so the kind of nice theory kind of is in like this vector space setting, I guess, like most of the ML stuff. So basically, you know, if you consider something more general, like you make the stocks just sets or topological space, let's say, or something, you have continuous functions that are arbitrary. For instance, you don't, you know, how do you define Laplacian anymore and things like that. So you have like basically some category theory constraints to define the Laplacian, because you need this kind of adjointness to have, because you have that coboundary transpose times coboundary. So what does transpose mean, right? So you need to work in a category where you actually have that notion of like, well, adjoint, basically. So that's kind of, you have some restriction on that side as well. So yeah, basically, if you use some very general categories, you might not have Laplacians. And actually, this is a very nice area of research. So Robert Grice has some papers now. I think it's called the Tarski Laplacian, which is just the Sheaf Laplacian when I think you use like lattices on these things and more obscure objects. But it's hard to find like maybe applications for some of these more kind of obscure things. But yeah, that's a big area of research, and I'm going to mention that at the end. Okay, so here's kind of how our model works. And before that, I also want to mention that actually Sheaf neural network started with this paper by Hansen and Gebhardt, which was, I think, accepted at some NeurIPS workshop like about a year before our paper came out. But kind of no one explored that. I think I was the only, like we were the only persons kind of citing that paper on, you know, like kind of topology papers you saw in the first part as well. And, you know, people were, I think, were kind of ignoring, or it kind of went unnoticed. And part of that reason was because they were handcrafting these Laplacians. So, you know, they had to use this very synthetic example where you kind of knew how you should design it to do well. But, you know, in practice, how do you do that? Because you don't have a sheaf. So, okay, let me finish because I promised I finish early. Okay, so, yeah, so basically we just have a diffusion, sort of a generalized diffusion process. So what we've done, we just put some extra weights before and after to multiply our features, essentially. And what you could think of this part, what it's doing, you just take W1 and multiply all these d-dimensional vectors that we're stacking. So it's kind of just, because we have vectors, now we can also multiply them from the left. Before in GCN, these were just scalars. So, you know, this would be a scalar then. So you just put it in W2. Okay, so this is a bit more general. It's not like exactly diffusion, but it can be reduced to that. So, you know, if you make this identity and you make this also identity, you just get the diffusion equation. Okay, and in practice, we actually use a discrete version of this. So you just take an Euler discretization, and that's kind of more efficient to compute. But this has kind of like, you know, the discrete diffusion process has kind of the same convergence property. So, okay, and the main idea from this part, as I said, is we learn the sheaf from data, and actually for that reason, you can apply this to any graph data set. And I was saying like this, you also need to kind of be careful about encoding your features initially, as Michael was asking, but that's easy to do. So in general, you have no restrictions applying this to anything you like. And I also want to mention briefly this recent work by by Federico Barbero, who actually just presented this at an ICML workshop on topology and geometry. So here, but we're kind of exploring as an alternative to what I've just said about learning sheaves. There's a way to just infer some sheaf at pre-processing time. So if you assume your graph comes from a manifold, then essentially you can use some existing tools. So for kind of building connection Laplacians from this paper that we sort of adapted for graphs, and you kind of find these kind of transport maps between vector spaces that best align your kind of tangent spaces there, and these tangent spaces are given by doing some PCA in that local neighborhood. So yeah, check that paper if you want to find this kind of alternative approach, and this kind of lets you use the Sheaf neural networks a bit more out of the box. So like you don't need to use any, you could just have a GCN but with sheaves, right? You just use this Laplacian essentially, but so and kind of transferring many existing models to these things. Okay, so.
Okay, sorry, so just about the question, comments on this is also what I was asking Federico. So in the original motivation for the paper of Zinger, right, about connection of Laplacians was a kind of synchronization problem, so you can apply a rotation transformation at each node of the graph. So basically, you have these OIJs that are a product of rotation matrix OI and OJ transposed. So what does it mean geometrically in this case? So would it assume some flat geometry or not necessarily? If you can factorize all IJs into OI OJ transpose.
I'm not sure about that, but yes, like essentially these are in some sense less expressive than what we kind of learn, because these just comes, you'll just have an orthogonal matrix for this space, one for this one, and then you multiply, as Michael was saying. So yeah, the question was like, what sort of happens in this kind of setting, and indeed it's in some sense less expressive because you have this factorization, and that kind of constrains your orthogonal maps. So I think probably kind of maybe even considering like more advanced versions of this for the future, maybe with extra assumptions, and also show we haven't proven this sort of makes sense if you take like some limits or something and kind of make this infinitely small. I think that could be nice, to show that this is actually a good thing to do. Okay, so just to see some results, I have just 2 more slides and I'm done. So first, just to see that essentially here's just a bipartite graph. And if we use Sheaf diffusion, as time goes towards infinity, essentially our performance improves. And we also looked at how these maps that we learned look like. So, and you can see that the model actually learned to invert the features like in this kind of -1, 1 setting that we saw. That's exactly what happens here. The model actually learned that I should just invert the features of the 2 partitions to polarize the opinions like we saw before. Okay. And then we applied this to just some real-world data sets, and it was doing pretty well. And the colored ones are kind of the top 3 results. And in the heterophilic graph, so this is from heterophilic to more homophilic, in general, we were doing quite well in the heterophilic ones and pretty much on the top 3 for almost all benchmarks. Okay, and at the end, just want to say that there's also the category theory perspective, where we can literally, just by choosing this category D, we can have any sort of structure, not just vector spaces, but anything. And kind of going to that is the big thing, like one of the big directions in this area. Okay, so I finally just want to say that this is actually the result of many collaborations. So the things you saw in the first part were kind of papers together with Fabrizio from Twitter, and what you saw like now was collaboration with Francesco, and then there's the paper from Federico that I mentioned, and then there's also Yugong Wang, Guido Montefar, Nina Otter, Ben Chamberlain, Michael, obviously, and my supervisor Pietro. As you can see, I collaborate with lots of Italians. I think the Italians dominate this list for whatever reason. So, okay, thanks for your attention. That's it. Sorry for going over time.